So this is another geometric proof problem, and this time we're dealing with a triangle, and we're told a bunch of things about it at the very beginning. In this opening paragraph right here, this is basically a description of the picture that's drawn below. And I want to address several points in turn. One is that A, B, and C are collinear, and C, D, and E are collinear. So let's talk about what that means. It just means that these are all in a line, and it means these are all in a line, which you could tell from the picture. It also tells us that BE and AD, okay, here's BE and AD, they intersect at this point F right there. So that's useful information. And the last piece of information is the most important. AB is congruent. This symbol right here means congruent. And what congruent means in geometry is it means geometric shapes are equal to each other. That's why it looks so much like an equal sign. So what we're saying is that this distance, AB, is equal to this distance, BC. And that's equal to CD, and that's equal to DE. Okay, so that's the key of this problem, really. That's the most important piece of information we have here. Now, let's talk about what that means. There is something in geometry called the angle bisector theorem. And we're going to use this to solve this problem. The angle bisector theorem says that if you have a line, and I'm gonna use this one right here. Let's say we have that angle that I drew in red, and you have a line that cuts it in half. If this line cuts that angle perfectly in half so that these two blue angles are equal to each other, then as a result, these two lines right here must be equal to each other. Well, we already knew that those two blue lines that I drew, CD and DE, are equal to each other, right? That's what these blue tick marks here mean. They mean they're equal. So if those two lines are equal to each other, it means these two blue angles that I've drawn over here are equal to each other, right? This angle right here and this angle right here. So we've just done the angle bisector theorem in reverse. We looked at two equal lines, and we said the angles corresponding to those equal lines must be equal to each other. And that is extremely useful information. So let's get rid of these guys. And I'm just going to stick with those two equal angles now. If I have those two equal angles, and by the same argument, these angles must also be equal because of the equal sides on this side of the triangle. What I can even say is that all these blue angles that I've drawn here are equal to each other because all those lines are equal to each other. This line is equal to this line is equal to this line, right? There's a lot of symmetries all over this triangle. So these angles that I've drawn in blue are all equal to each other, meaning the triangle AFE, if you look at where triangle AFE is on this figure, that is an isosceles. That's an isosceles triangle. And we're going to use that to figure out what we need. Okay, so there's still one piece of information I haven't talked about yet, which is that angle AFE is 116 degrees. That's this right here. So if we have an isosceles triangle and angle AFE is 116, we know that 180 degrees equals angle AFE, that's 116 degrees, plus these little blue angles in here, which are equal to each other. And I'm going to say, well, let's just call those x, plus x, plus x, okay? And we can use a calculator to figure out what x is, right? We just do 180 minus 116, and that's going to give us 64 degrees equals 2x. So divided by 2, and we get 32 degrees equals x. So what we want to do is now use that information about x to figure out angle CDE. And I'm going to draw angle CDE in purple here. Where is CDE? Oh, CDF, sorry. CDF in purple. That's what I want. So CDF in purple is this measure right here that I'm drawing. That's what I want. So to figure that out, wouldn't it be helpful if we knew this angle right here, angle FDE, And to figure that angle out, what I want you to do is imagine this triangle that I'm drawing now in magenta. Okay, see this triangle right here? We know several angles in it. We know this angle right here. We know this angle right here because that's the sum of x plus x. So this picture's getting a little crowded. Let me try to draw that shape over here. So I'm going to go back to magenta. My triangle that I'm trying to draw here has an angle of 2x right there and a single x right here. And I know because the sum of an angles of a triangle is 180, this is going to be 32 degrees plus 2 times 32 degrees plus angle FDE. Okay, FDE is this thing that I'm talking about right here. And we can use a calculator to figure out FDE. We do 180 minus 32 minus 2 times 32. So that tells me that this is 84 degrees right here, this angle FDE. And the useful thing about angle FDE, right, that's this guy right here that I'm drawing. If I know that, I know the purple angle that is supplementary to it right here. So if I add up angle FDE and angle CDF, CDF is what I want, that's what I'm looking for, that sum has to be 180 degrees. So what we're saying is 84 degrees plus this thing that I want is 180, so I just do 180 minus 84. 84, which is going to be 96 degrees. Okay, so that is your answer. Now, just because I was able to solve it in this case doesn't always mean you can solve these problems. Honestly, every now and then, you're going to get some mean test where they don't give you enough information, and that's a possibility. But in this case, the key solution to this came down to the angle bisector theorem. That's what helped us out here.